Okay, hi guys. So in the last video, we looked at composite functions, and now we're going to be looking at inverse functions. So first thing you have to notice is inverse functions have the notation f negative 1x. And so I'm going to give an example of how to solve for it. So let's say you had the function f of x is equal to 3x minus 7. And we wanted to find the inverse. So we wanted to find f of negative 1 of x. So first thing we have to do is substitute f of x as y to get this, as y and f of x are pretty much interchangeable, except f of x allows you to use composite functions, for example. So y equals 3x minus 7, then rearrange to find x. So we get 3x is equal to y plus 7, and x is equal to y plus 7 over 3. And now, upon doing that, substitute into x f of negative 1 of x, since we want to know the inverse, and substitute x in terms of y. So we get, after all that, f negative 1 of x is equal to x plus 7 over 3. So that is our inverse. And the principle behind inverse is that with this function, right, if we were to expand the processes that go behind it, you have your input, which we can say here is x, right? Then you times it by 3, which you get 3x. And then you minus 7, which gives you 3x minus 7. And what you should be able to do is go the exact same way back using the inverse. So if we took 3x minus 7 and we used the inverse method of doing this. So 3x minus 7, we would first have to add 7. So we'd get 3x. And then we'd have to divide by 3 to get x. And this is exactly what the inverse over here is showing. And this is the algebraic way of solving it. The other way we can solve for an inverse is if we have a graph. Oops. Let me draw a straight line. So we have a coordinate plane like this. Not very good, I know, but it'll do. And let's say we have the line, y equals x squared, but we'll restrict it to only above 0 just for the purposes of this. The inverse of that is y equals root x, which looks something like this. The way you can find out the inverse actually is if you graph it against y equals y equals x, something like that, it's reflected. The two lines, as you can see, are reflected across this line. So that's the graphical way if you want to just see it. Now, coming back to my example of y equals x squared, and you notice how I changed the domain so that x is greater than 0. The reason I did this is because y equals x squared without this domain actually does not have an inverse. So if you were to draw a coordinate plane, oh no, that's a bad line, sorry. And if we graph y equals x squared, we can see that it's many to 1 because for two different inputs, there is a common output. Oops. You get the idea that the y value matches up at the same point here for two different inputs. This is why it's a many to 1 function. Now, many to 1 functions do not have inverses. The only functions that have inverses are 1 to 1. And the reason for this is because if we were to find the inverse of y equals x squared, we can graphically see that it's reflected across the y equals x line. It would look something like this. And as we know, this over here is called a one-to-many function, as for many y values, you get a common x value. And the issue with this is one-to-many functions are not functions at all. And as we established, only one-to-one and many-to-one functions are actually functions. So that means that the only functions that can have inverses are one-to-one functions. So the way we can actually make y equals x squared be suitable to have an inverse is establishing a domain. So over here, if we make y equals x squared, where x is greater than 0, the x is greater than 0 part will look something like this. And this, as we can see, is a one-to-one function, so that's acceptable. Likewise, we could even establish as x is less than 0, in which case we'd be left with this part, which is also a one-to-one function, and therefore also has an inverse. So the criteria for having an inverse is that it must be a one-to-one function. It cannot be a many-to-one function, as it will have a one-to-many inverse, which is not a function at all. So the inverse has to be a function, and for that to happen, there must be a one-to-one function. So thank you so much for watching, and hope this helps. Let me know in the comments if you need any help with this whatsoever, because it took me a while to understand this concept of why this has an inverse and why this doesn't. But anyway, thank you, and see you in the next one.